Okay, so we've talked about the models of acids and bases. Let's do a couple more vocab terms and then we'll dive into pH. So the first vocab term I want to talk about is monoprotic acid. A monoprotic acid is exactly what the term mono means, and protic means, kind of combined. Mono means one. Protic is basically looking at the proton or hydrogen. Remember, hydrogen is synonymous for proton. Reason being, if we go back and look at a hydrogen 1 atom, if you will, okay, it has a mass of 1. That means it also has atomic number. It has 1 proton. It has 0 neutrons. And it has 1 electron. If we remove that electron because it's stolen from a chemical bond, such as the anion stealing it from hydrogen, the only thing that's left is a proton. So protic or proton are used kind of synonymously for a hydrogen ion, also hydronium. So you kind of have 3 words you have to keep up with here, and I apologize for that, but that just is what it is. But these are all 3 synonymous. Proton, hydrogen ion, and hydronium ion are all kind of being used interchangeably throughout acids and bases in general. So a monoprotic acid is a species that has 1 hydrogen in it and it gives up that 1 hydrogen. Versus diprotic would be something that has 2 hydrogens, and what it's going to do is it's going to give away each hydrogen in a stepwise fashion. So it's going to get rid of the first hydrogen, leaving HA minus, and then HA minus would then give up the secondary hydrogen, leaving A minus. This is very common with acids like H2SO4. H3PO4 would be a triprotic. So it would give up 3, so it would have 3 steps. So it would have H3PO4 going to hydrogen and H2PO4 minus, and then H2PO4 minus goes down into HPO4 minus 2 plus a hydrogen, so on and so forth. So each time it's getting rid of another hydrogen. Something to keep in mind is as it's losing a hydrogen, the acid is getting weaker. So H2A is a stronger, we're not going to use the word strong because we don't actually know how strong it is, but is a stronger acid than HA minus. So each consecutive hydrogen that is lost or proton that is lost, the acid does get weaker and weaker and weaker, and that's going to affect some of the math we do in a little while. Then we have this term amphoteric. This is very important for water, and is why water is allowed to be a Bronsted-Lowry acid and a Bronsted-Lowry base. It's able to do both because it can both gain and lose a hydrogen. That's what amphoteric means, is it can act like an acid or a base. And the reason to access one or the other is dependent on who it is combined with. So if I was to add an acid with water, water is going to act like a base. So it's going to steal the hydrogen, forming H3O and chlorine ions. Versus if I was to react it with a base, it's going to act like a acid by giving up the hydrogen, forming NH4 plus and OH minus. So we kind of have this idea of species being able to act like both. And again, it's very dependent on what it's with. Even some of these guys that are diprotics up here can act amphoterically. So for example, one of the big ones in our bloodstream would be this thing's kind of freaking out, HCO3 minus. This guy has the ability to gain and lose a hydrogen, so he will do both to buffer, which we'll talk about buffers a little bit later, our bloodstream. And we also have this term autoionization. This is what happens in a solution of water. Water is ionizing in itself into hydronium or hydrogen ions and hydroxide ions. Why is that important? That is going to lead us to understanding pH and what pH actually is and where it comes from. So pH and pKW comes off of, or pH comes from this idea of KW. K, again, is an equilibrium expression. W means it's standing for water, so no big deal there. But what we're looking at is pure water, so there's nothing else in this water right now, and it's ionizing itself. And what it's doing is it's creating hydrogen ions and hydroxide ions are hydronium and hydroxide, however you want to think about it. So our reactants are pure liquids, so we're not going to include them in our equilibrium expression. So what we get are just our products, which could also be H3O plus and OH minus versus just hydrogen plus and hydroxide minus, but either way. This guy is called Kw. Kw is actually what determines our pH scale as well as our pOH scale. And this reaction is what allows us to kind of understand acids and bases a little bit better. So understand with this, our mole ratio, how many hydroniums are being produced for how many hydroxides? Well, it's a 1-to-1 ratio. For every hydronium that's produced, there's one hydroxide that's produced, which means at any given point in time in pure water, the concentration of hydronium is equal to the concentration of hydroxide, which means we end up with what is called a neutral solution. At any point in time, if this hydronium ion concentration was to increase, we would end up with an acidic solution. If hydroxide was to increase, we would end up with a basic solution. So it's whichever species is more prevalent in solution is what causes our solution to either be considered acidic or basic, or if both are equal, it is neutral, and it is common to have a neutral solution. So what we end up with is Kw equals the concentration of the hydrogen or hydronium ion times the concentration of the hydroxide. And through experimentation at room temperature, 25 degrees Celsius, we're able to calculate the concentration of hydronium and hydroxide as 1 times 10 to the negative 7th. And therefore, both of them equal. Therefore, Kw is equal to 1 times 10 to the negative 14. So what does all this have to do with anything? We're going to assume that all of our solutions are occurring in this unit anyways, at 25 degrees Celsius, room temperature, because of this standardization. So keep in mind, if I change temperature, I do change my Kw value, which does actually change what pH is. A pH of 7 at negative 25 degrees Celsius doesn't actually mean the same thing as pH at 7 or 25 degrees Celsius, of 7 at 25 degrees Celsius. Because remember, K is temperature dependent and pH is based off of these values, which is part of our K. So what I want us to check out, we have our pH and pOH scale. So blue is commonly used for hydroxide and red is commonly used for acids. So we have our scale going on here. Remember, acids start at 0 and they go to 14. Bases, actually for the same scale, but we would have 14 going to 0. So this is our pOH scale. This is our pH scale. And notice what's happening here. As the hydrogen ion, the thickness of the triangle basically is representing the concentration of the hydrogen ion, or the hydroxide ion. As hydrogen ion is increasing, what's happening to our hydroxide ion concentration? Well, it's decreasing. Well, why? Mathematically, it's because Kw equals the concentration of hydrogen times the concentration of hydroxide. If I was to increase my hydrogen ion concentration, Kw is a constant, hydroxide has to decrease, and vice versa. If I was to increase my hydroxide ion concentration, Kw is constant, hydronium, or hydrogen, has to decrease. And we see that as we go up the scale, hydroxide increases, hydrogen decreases. This is what creates an acidic or basic solution. So if I was to add an acid to water, it would increase my hydrogen ion concentration, because acids produce hydrogens, and therefore decrease my hydroxide ion concentration. If I was to add a hydroxide or a base to water, such as sodium hydroxide, it would increase my hydroxide ion concentration and decrease my hydrogen ion concentration, resulting in a basic solution. So that's kind of the only difference between acidic and basic, is which species is more prevalent. Now, here's the next thing. pH, if we were to go through and actually look at the equation for pH, pH is looking at logarithms. Okay, and what is pH? pH is just a way that we use to really look at the power of the concentration of hydrogen and hydroxide. So remember, the concentration of hydrogen in a neutral solution is very, very small. Let's see if it will let me write. There we go. The concentration of hydrogen in a neutral solution is 1 times 10 to the negative 7th. So it's not very big. So what we're actually looking at is this guy right here, power, pH. P doesn't technically mean power, but a lot of times people will say it is. We're looking at the power of the superscript, or of the power of the times 10 raised to, the exponent. There's the word I'm looking for. So this exponent actually is what allows us to determine our pH readily without any math involved, or using mental math. Remember, multiple choice, you don't get a calculator. So like if I told you the hydrogen ion concentration was 1 times 10 to the negative 3rd, we could say our pH is 3. Pretty easy. In a neutral solution, since our hydrogen ion concentration is 1 times 10 to the negative 7th, our pH is equal to 7, or what we consider neutral at 25 degrees Celsius versus our pH of 3. Now, with that in mind, if I was to calculate Kw, because hydrogen ion is equal to 1.0 times 10 to the negative 7th, hydroxide, using my Kw expression, Kw equals 1 times 10 to the negative 14th, times hydrogen times hydroxide also equals 1 times 10 to the negative 7th. So not only is my pH equal to 7, but my POH is also equal to 7. And if we go back and look at that scale, that's right in the middle of those two values. Scroll down real quick. Look at that. So like 14 to 14, right in the middle of that would be 7 for our pH, for both of them, for both pH and POH, and that is our neutral, or when all of the concentration of, or when the two concentrations equal each other. Okay, so let's kind of keep looking through this. So pH calculations is the negative log of the hydrogen ion concentration. So what this is actually doing, what the log is doing, is getting rid of this times 10 raised to, and we're looking at just the exponential aspect of it as well as the concentration, the initial aspect of it. So we're looking at this and this piece of it. So that's why we're able to make those assumptions pretty readily without having to use a calculator. As long as we know what this power is, we can pretty well make an estimate of what our pH or POH is going to be. In terms of sig figs, something we'll discuss as we go through, your sig figs are kind of weird with these. However many sig figs are in your concentration is how many go after the decimal in your pH, and a lot of that has to do with this exponential form and how it's working. Okay, so kind of going through this again, are looking at how Kw applies to all this. Again, Kw equals concentration of hydrogen times concentration of hydroxide. If I was to increase one of these, I would have to decrease the other one, and vice versa. We can then take the negative log of all of this, or the P, and we get pKw equals pH plus POH, which gives us this beautiful equation right here. pH plus POH equals 14, which means as I decrease my pH, let's say my pH is 1, my POH would increase to add up to equal that 14 value. So we'll go through and play with some of these as we move through this, but essentially what I want you to recognize is pH and POH are simply based off the hydrogen ion and hydroxide ion concentration. Both are always present in an aqueous solution, whether it is an acidic solution or in a basic solution. If it is acidic, we have more hydronium, less hydroxide. If it's basic, we have more hydroxide than we do hydronium. But again, both are present to some quantity. That quantity is based off the Kw of the water at 25 degrees Celsius. And we can use that information to calculate pH and POH. And by the way, your POH looks exactly the same as this. POH, here, let me write it out for you so you can see it. POH equals negative log, and instead of taking it of the hydrogen ion concentration, we take it of the hydroxide ion concentration. And again, we would know which one to calculate based off of which species we knew. So if we knew hydroxide, we'd be calculating POH. If we knew hydrogen, we'd be calculating pH. And of course, which one do we use? We use pH. We very rarely ever use POH, but we do have to calculate using POH on a regular basis if we got a basic solution. But then we just convert to pH using our pH equals POH, pH plus POH equals 14 equation. All right, so that's it for right now. We're going to go through and practice this though, so this is a little overwhelming. It will be better once you see it. Thanks, guys.